Hello, everyone. I'm going to go ahead and get started, I think. Okay. So this is CHL 41 period 7. Okay. So what we're going to be talking about today is Ampere's law. We're going to be doing various examples with Ampere's law. And so just to remind you what Ampere's law is, we have the line integral of the magnetic field around a closed loop. That loop is called an Amperian loop. Is equal to mu naught times the current enclosed by that loop. Okay, so let's break it down. What does the left-hand side of this mean? Well, if you have some loop, it's going to be made up out of various segments. Okay, and we could number each of those segments. The loop has a direction. Okay. Like that. And so on each segment, the magnetic field has a certain value. So it's like, here's the magnetic fields, and it has a certain angle relative to the direction of the loop. And so what the line integral is we take the vector that points along an individual segment, the length vector of that segment, and we take the dot product with the magnetic field on that segment, and then we add up all of the segments. Okay? Now, if you have cylindrical symmetry for the problem, then the magnetic field lines are going to make, so I'm going to put cylindrical symmetry. So if you have cylindrical symmetry, then the magnetic field lines are going to make circles. Okay? So you have circuit. Circular magnetic field lines, and then your Amperian loop is also going to be a circle, which we can think about as just a single curved segment. And so what you get is just B times 2 pi r if there is cylindrical symmetry. So 2 out of the 3 examples that we do today are going to have cylindrical symmetry, and the third will not. So I'll show you how to do an example where there isn't. The current enclosed is an integral that depends on the current density. So current density, remember, is current per area. So it's J times 2 pi r dr. All right. So there you have it. So let's go ahead and start our first example. So what if we have a tube of current with cylindrical symmetry? All right, so I'm going to show this tube from a front view. All right, oops, I'm drifting off here. I want to check this email. Just give me a second. That's not the email I wanted. Okay. So anyways, so it's a tube of current like that, and it's a thick tube. All right. So the tube extends from r equals a, so the inner radius is a, and the outer radius is b. Okay, and so the current only exists in this region in between the that's inside the tube. So this tube has cylindrical symmetry, right? So it's coming out of the page like so. I'm making a cylinder out of paper, so it extends forever and ever out of the page like that. Okay. The current density within the tube is equal to some constant, which I'll call C, divided by R. So what that means, because 1 over R is a decreasing function, that means that there's more current on the inner wall of the tube. Okay, so I don't know why I'm spending the time to draw this, but why not? And then that amount of current gets smaller as you approach the edge. So maybe like that. Okay. And so obviously this current only exists when R is between A and B. Okay. And then it's 0 everywhere else. So what we want to do is we want to calculate the magnetic field as a function of R, and then graph it. So there are going to be 3 regions where we need to calculate the magnetic field. So the first one is when R is less than A. The second one is when R is between A and B, and that's going to be the toughest one. And then the third one is when R is greater than B. Okay, so anytime we have a problem where it has these sort of layers like an onion, we have to analyze the problem in each region separately. Okay, so if R is less than A, because we have cylindrical symmetry, the magnetic field lines are going to make circles. So magnetic field lines make circles. And our Amperian loop is also going to be a circle. And so that is why we get the left-hand side of Gauss's law will be B times 2 pi r. So let's look at this Amperian loop if r is less than a. And remember, the radius of the Amperian loop is the radius at which we would like to calculate the magnetic field. Okay? So if that's our Amperian loop, notice how it doesn't enclose any current because the current starts here at r equals a. So the current enclosed is 0. Okay. And so we can see that the right-hand side of Ampere's law is 0. And so that means that the left-hand side also has to be 0, which means that the magnetic field is going to be 0. Okay, so inside the tube, we have magnetic field is equal to 0. That was easy. Okay, so what if R is between A and B? So in this case, for our current enclosed, we have to actually do the integral. So remember, it's the integral of J times 2 pi r dr. So J is C over R, and then I have 2 pi r dr. So what are our limits of integration going to be? Well, we can't go from 0 to little r, okay? Because the current doesn't start at 0. The current starts at radius a. So our lower limit of integration is going to be a. And then the upper limit is going to be r, where r is the little r. I'm using big R and little r just because it's a little bit messy when you have the integration variable is the same as the limit of integration. So, so our Amperian loop is kind of like here. It's enclosing a little bit of the current. Okay, and so that will be our limit of integration. So notice that we have r in the numerator and r in the denominator, so they cancel out. And so this is integrating a constant. All right. So, and just to remind you, if you have the integral of dx from a to b, the answer to that is going to be b minus a. All right. So for the current enclosed, we have 2 pi c, which is the constant, times r minus a. All right. So then when we go to Ampere's law, the left-hand side of Ampere's law is B times 2 pi r. The right-hand side of Ampere's law is mu naught times the current enclosed, which is 2 pi c times r minus a. 2 pi's cancel out. Divide both sides by r. So we get B equals mu naught times C times 1 minus A over R. So how did I get that? When I divided by R, I carried it into this term. And so R over R is 1, and then A over R is A over R. So that's how I got that. So this is the magnetic field in the second region. So now let's look at the third region. So for the third region, the radius of our Amperian loop is bigger than B. So that means that the loop is all the way out here. Okay, so there is the loop, right like that. So we redo our calculation of the current enclosed. So it's going to be 2 pi c times the integral of dr. Remember that r canceled out so that there is no variable that we're integrating. Our lower limit is a. Our upper limit can't be little r anymore. Why? Because the current stopped at radius b. So even though the Amperian loop is bigger than that, we can't go beyond b as our radius if we're counting up the current, if we're adding up the total amount of current, okay? Because the current stops right there at the outer edge of the wire, of the tube, I should say. All right, so this is going to be 2 pi c times b minus a. All right. And so then Ampere's law, the left-hand side, is b times 2 pi r. The right-hand side is mu naught times 2 pi c times b minus a. 2 pi cancels out, and we get that b equals mu naught c times b minus a over r. Boom. Okay, so let's see, what do each of these graphs look like? And then we're going to stitch them all together. Okay, so remember, we're going to make a graph of magnetic field versus R. And there are 3 critical regions. There's R equals A, there's R equals B. And then so it's this region, that region, and this region. All right. So the graph of B equals a constant divided by R, that one's really simple. It's just going to, if you do y equals 1 over x, all right, it just looks like this. Okay, so that shape of graph is really easy. This one might be a little bit trickier for you to see, so let me show you. Notice how we have constant over r. All right, so if we do constant over r, it looks like this. But then we do negative a constant over r, so then that's going to look like this. And then we add a number to it. So that's going to shift the graph up. And so we get something that kind of looks like this. All right. So that's what the graph is going to look like in the second region. And then this region is very simple because it's just 0. So the magnetic field is 0. And then we enter this region where the magnetic field has that sort of shape. So the magnetic field is going to grow like that. And then we enter the third region where the magnetic field does that. I'm getting a call from the principal. Hang on. Hello, Dr. O'Connor. I'm live streaming right now. Okay, will do. Oh no, am I going to get in trouble for my April Fool's joke? All right. So, anyways, that is that graph. So now let's go ahead and look at the next example, a wire let's see, a wire of radius A carries a total current I, and it carries that current uniformly. All right. So here we have the here's the wire. It has radius A. All right. And so what I want to do is I want to calculate the magnetic field as a function of R, and then I want to graph it. All right. So because it's a uniform, it's uniform current density, constant current density. So that means that the wire has an even current throughout. And so in that case, it's really easy to calculate the current density. The current density is just going to be total amount of current divided by total amount of area. It's a circular cross section, so just pi r squared. So that's a constant. And so we have two cases. The first case is when R is less than A. And in that case, you have an Amperian loop that is small. Like that, okay? And then the second case of interest is when you have R greater than A. Like that. So, the current enclosed is going to be the integral of J, which is a constant, times 2 pi r squared r dr. Okay, the pi's cancel out, and we would get the integral, and then I'm going to factor out all the constants, so I get 2i over a squared times big R dr. So in the case of R being less than A, our integral is going to go from 0 to little r. All right, and this gives the value for the current enclosed is going to be I times r squared over a squared. Okay. So then when we go to Ampere's law, what we would get is, so the left-hand side of Ampere's law is B times 2 pi r, and then the right-hand side is mu naught times the current enclosed. So this factor of r cancels out one of those, and I get that b equals mu naught I r over 2 pi a squared. So this is the magnetic field inside the wire, and we can see that it depends linearly on r. So that magnetic field as a function of r is going to look like this. Okay? And then once we're outside the wire, r greater than a, the current enclosed, we don't even have to do an integral because we're enclosing all of the wire. And I said that the wire carries a total current I. So it's just, that's the answer. And then I go to Ampere's law, B times 2 pi r equals mu naught times the current enclosed, which is all of the current. So I get B equals mu naught I over 2 pi r. So that is 1 over r, which is going to look like this. So when I stitch it together, my magnetic field is a function of r. Here's A. It's a linear dependence. And then an inverse dependence, like that. So that's what the graph would look like. All right, so those were two where we had cylindrical symmetry. So let me show you one where you don't have cylindrical symmetry. And that is a so-called solenoid. Okay, so what is a solenoid? It's basically a curlicue of wire. Okay, so if we were to look at a solenoid from a side view, it's like that sound effect. And then if we were looking at it from the front, okay, all we would see, it's a curlicue, so we just see the circles that the wire is making, so it just kind of looks like this. Okay, and then we could do sort of a side cross section. So we can imagine taking the solenoid and sawing it down the middle. And so what we would see is the wire coming out of the page, and then the wire coming out of the page and then circling around and going back into the page, like that. Okay, so I'm going to draw this a little bit bigger, and let's try to figure out how does the magnetic field of a solenoid look. How do the magnetic field lines look? 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if we look at using the right-hand rule number 2, we put our thumb out of the page, okay, for, like, say, for example, this wire that's going out of the page. So I put my thumb out of the page like that, and then my fingers are curling in the sense of the magnetic field. So that gives me a counterclockwise magnetic field from that wire. And then I could do the same thing for this wire and all of the wires. All the wires on top are making counterclockwise magnetic fields. Okay. Now for the bottom row, we have thumb into the page and our fingers are curling in the in the clockwise sense. So now we get something that does that. So if we look inside the solenoid, so when I say inside, I mean kind of like in this region, all of the magnetic field lines are pointed to the right. Okay? And so what that means is that the magnetic field lines inside the solenoid are just kind of all going to the right. And because there's not a lot of space inside the solenoid, the magnetic field is like more or less constant inside the solenoid. Okay? And then once we get, now remember, magnetic field lines make loops. So once we go outside the solenoid, those magnetic field lines have to loop around. And so they kind of go like this. And I'm not even going to draw the entirety of this one just in the interest of space. There's this one. Like that. Okay? And so we can see that the magnetic field lines are emerging from one end of the solenoid. Okay? So that's the North Pole, and then they're going into the other end, the South Pole. So that's what the magnetic field lines look like. And a couple of observations. Inside the solenoid, you can see that the field lines are scrunched together. Okay? So we have a strong magnetic field inside the solenoid, and it's more or less uniform. All right? Meaning constant, no matter where you are inside the solenoid. Outside, the magnetic field lines spread out once they exit the solenoid, okay? And so the magnetic field is weak outside of the solenoid. It's so weak that we are going to say that it is approximately zero, okay? So we are going to apply Ampere's law to this. And so the loop that we're going to use is not a circular loop for this one. It's a rectangular loop. And I wish I had a different color to make this a little bit clearer. But it's a rectangular loop, okay? And we're going to give it 4 segments. So there's segment 1, segment 2, segment 3, and segment 4. And one thing I forgot to do at the beginning of this discussion of solenoids is I forgot to tell you the variables involved. So N is the number of loops that the solenoid makes, and then L is the length of the solenoid, okay? So when I do the line integral of B, it's going to be B1 dot L1 plus B2 dot L2 plus B3 dot L3 plus B4 dot L4. All right. So if we look at segment 3, which is, so actually 3 of the 4 terms are going to vanish, okay, and I'll explain why. Segment 3 is here, and it is outside the solenoid. So the magnetic field is approximately 0 outside. So that means that this term is negligible, okay? segments 2 and 4 have a length vector that go vertically, but we can see that the magnetic field is basically horizontal at that location. All right, so we have a length vector that is going up, and we have a magnetic field vector that is going to the side. It's about a 90-degree angle between them. So theta equals 90 degrees, which implies that cosine of 90 degrees is 0. And so, because remember, dot product is magnitude of first vector times the magnitude of second vector times cosine of the angle. So these two terms drop out. So the only segment that contributes is the first segment. And this segment has theta equals 0 because the magnetic field points to the right, and the length of the loop segment points to the right. And cosine of theta is going to be 1 in that case. So then I get B dot L is just B times L, where L is the length of this loop, which also is the length of the solenoid. Okay. So the right-hand side of Gauss's law is just B times L. That's the integral, or the left-hand side, excuse me. Integral of B dot dl. Now let's look at the right-hand side, which is the current enclosed. So even though this wire is carrying just a single current I, that current is passing through the loop multiple times. And each time it passes through, we count it again. So the current enclosed is N times I. All right. So then I can go to the full Ampere's law. Line integral of B dot dl is equal to mu naught times the current enclosed. This line integral we just said was B times L. Current enclosed is N times I. Divide both sides by L. We get B equals mu naught N I over L. Okay, so a question is, well, how do you maximize the magnetic field? Because this kind of geometry, a solenoid geometry, is essentially what an electromagnet is. Okay, so how do we maximize the magnetic field produced by an electromagnet? Well, we want the current to be big, and we want the number of turns per length to be big. But these are kind of competing factors, right? Because the bigger the current is, the thicker the wire has to be in order to carry that current safely. And the thicker the wire is, the less tightly you can wind it in a loop. Okay? Alternatively, the more tightly you wind the wire in the loop, the thinner the wire has to be, which means the less current it can carry. So you have to make kind of an engineering choice. Okay? There is one more thing, which is probably the most important thing if we want to maximize the magnetic field, is we can actually increase mu. Okay? Because mu naught is the permeability of free space. Free space. But what if we don't put free space in the solenoid? What if we fill it with something? Like maybe iron. Iron has a permeability that is different from free space. So the permeability, which is permeability in general is just mu, is actually much, much greater than the permeability of free space. Okay? And so that has the effect of enhancing the magnetic field. Basically, iron has the potential to be magnetic, and that potential isn't realized until it's introduced to another magnetic field. So iron is kind of like, I could be magnetic if there's a magnetic field around, but I'm not. And so once you use the current to put a magnetic field in the vicinity of the iron, then all of the iron is going to be like, all right, we're doing this. We're going to be a magnet. And then they all kind of like, the atoms in the iron all work together to enhance the magnetic field. So we often write, if it's a material that is not free space, we write its permeability as just mu, and it's equal to a constant times the permeability of free space. So this is called the relative permeability. Okay, so really there should be a mu sub r right here. Okay, so for example, if the relative permeability was 2, then mu sub r times mu naught is going to be 2 times 4 pi times 10 to the minus 7. Okay? So that was my lesson for today.